and recording of all those astronomical details. They're recognizing patterns, recording one-off events, and passing that history down through stories and song over thousands of years. So we have a really, lots of great events out there that we can track over time. And as technology progresses, we're tracking things even further and further out into space, which also means we're tracking things further back in time. So back to millions or even billions of years back in time with gravitational wave events. So in a sec, I'm going to hand over to Paul Lasky. He was right there in 2015 when the first gravitational wave event was detected with the LIGO collaboration with more than 1,000 scientists all around the world being super excited about it. Since then, we've added the Virgo detector in Italy and the Kagra detector in Japan. So it's a really exciting time for us to be involved, and we have more than 200 members of OzGrav in Australia. So it's very exciting to be involved in this collaboration, and there's heaps more to come. So I'm going to hand over to Paul in a sec. He would love to have your questions, so please type your questions into the Q&A box and we can get to those at the end. I'll leave it up to you. Thanks, Paul.
Great, thanks, Lisa. And thank you to everyone for coming along. I'm just going to share my screen and see if we can get this started. Thanks for the very nice introduction. I'm giving this talk about a proposed Australian high-frequency gravitational wave detector. And it's got a couple of different names, and I'm going to be talking about it, referring it to OzHF throughout this talk. And I'm really giving this talk on behalf of the entire OzGrav OzHF team, which is actually a very large fraction of the OzGrav team in general. So this is a project that's been going on for a little while now, and we've got the paper has been submitted, which covers a lot of the material that I'm going through today. And we hope to sort of have a bit of a press release and things, I think, next week to align with an astronomy decadal plan, which also prioritizes this project as well. So I'll sort of get to that as we go through, but I want to sort of provide a little bit of motivation for you as we go. And so I'm going to actually step right back and I'm going to introduce something that we don't often see when we hear gravitational wave talks, but this is a temperature versus density phase diagram that basically includes the entire universe. I think everyone can see my mouse. But basically, so what we're looking at here on the vertical axis is we've got the temperature and on the horizontal axis, we've got density. This covers a huge range. We live, somewhere right down in the bottom left-hand corner here. And particle colliders like the LHC probe increasing temperatures but still relatively sort of mild densities, at least compared to the densities that we're really going to be referring to throughout the talk today. So in particular, as I move along this axis on the horizontal, I get to a region of neutron stars. So I've got hadrons which is just sort of the usual matter that we think of in this sort of bottom left region. As I move up, we reach a phase where we may have this phase transition to what we get sort of deconfined quarks. So actual quarks that used to live inside the neutrons may actually drip out and be deconfined. And so neutron stars really live in this region of this phase diagram. But what's important now is that when I talk about neutron stars, I'm really referring to old neutron stars in this context. So old neutron stars are what we refer to as cold, and I put cold in inverted commas here because when I say cold, I really mean sort of 10 to the 7, 10 to the 8 Kelvin. But it turns out for a neutron star, that's really actually quite cold. A newly born neutron star can be much, much hotter than that, up to 10 to the 10, 10 to the 11 Kelvin. And that actually really takes us up off the bottom of this diagram and up into this region of phase space where I've put proto-neutron stars. And so you can see that because this phase transition, which is sort of a little bit theoretical, we don't know exactly where it happens, we don't know what densities and at what temperatures it happens. This phase transition happens in such a way that if I could have cold neutron stars that are purely hadronic, so they just consist of normal matter, but these proto-neutron stars could exist with quarks, deconfined quark states and things like that. So, this is really what I'm trying to get at here is actually looking at these proto-neutron stars and actually looking at neutron stars and the dynamics of neutron stars in general is really the only way in the universe to try and uncover this region of phase space diagram and actually perform physics experiments in this region of phase space. When you're talking about Large Hadron Collider and particle accelerators and colliders and things along those lines, you're really talking about these kinds of energies, but not bulk nuclear matter. You're not talking about the sheer mass of nuclear matter that we have. So the conditions are sort of very different. Obviously, the experiments are complementary and we need to be learning from one another. But really, neutron stars and proto-neutron stars are the only region of the universe in which we can attempt to really try and understand these regions of space. Okay, so that's sort of the real motivation for this in terms of the sort of fundamental physics. But what are the actual systems that we're talking about here? So what I'm going to show you next is a little simulation, which is actually a numerical relativity simulation of two neutron stars. So these two white blobs are two neutron stars that are being simulated. They're being Einstein's field equations of general relativity of evolving these neutron stars forward. And what I'm showing you on the horizontal axis here is the gravitational waveform that we expect to see. So you can see that as these two neutron stars spiral in on one another, it looks a little bit glitchy at the moment, sorry about that. I think that might be my computer. But as these two neutron stars spiral in, you get these nice gravitational waves, and then the two neutron stars merge. And in this example, at least, you end up with one neutron star that sort of survives for some period of time before it actually collapses to a black hole. And I'm not sure if you're seeing these glitches like I'm seeing it, but it's not looking as nice as it usually does. But anyway, in this example, let's move on so that we don't look at that too much. So in that example, what we saw was this gravitational waveform during this in-spiral phase. So this is a beautiful diagram that's been created by Carl Knox, who I believe is actually on the call as well. And it's going to appear in a review article that Nikhil Saran and I are writing at the moment. But during this in-spiral of the two neutron stars, as they get closer and closer together, they're emitting these gravitational waves, and we detect those gravitational waves. And what I'll talk about very soon is that we've actually detected gravitational waves from maybe 2, maybe 3 of these systems already. And in the near future, we're going to be detecting a lot more. But this diagram really shows then the range of possibilities that you have after that merger. And so in that, you can actually immediately form a black hole, or you can not. You can form a pseudo-stable neutron star, which is really massive, or even an infinitely stable neutron star. So let's actually walk through this diagram in a little bit more detail. So as I mentioned, this early phase is where we get these gravitational waves that we've actually already detected. And again, I'll talk about this very shortly. But what I'm showing here on the bottom axis is this gravitational wave strain. So the gravitational wave signal that we see from this in-spiral phase is these sort of undulating or oscillating signal. The amplitude you can see increases. Okay, so I'm showing two different signals here, and I'll in black and in red, and I'll explain what they are in a second. But the amplitude of this signal increases as the two stars get closer to one another. Their frequency increases as the stars get closer to one another and as they start moving faster and faster and faster. And this is that characteristic chirp signal that we're used to hearing about from gravitational wave astronomers. But what's really important for this talk is that if I were to have two black holes, then this is the red signal. So two black holes in spiraling has a certain very characteristic evolution of that gravitational wave signal, or the gravitational wave phase evolves in a certain way. But when I have two neutron stars, that gravitational wave signal actually changes. And it changes in such a way that you can actually go back and measure how sort of fluffy the neutron star is. And you don't typically think of fluffiness of a neutron star, but really that fluffiness that I'm talking about is how compact a neutron star is. Okay, and the compactness of a neutron star is to do with the equation of state. So this is really to do with the actual nuclear physics of the neutron star, which is that thing that we're trying to understand. It's that part of the phase diagram that we don't get, but we're really trying to probe and trying to understand. So from that in-spiral, we can start to understand a little bit about that, the equation of state, and we get to that through this quantity called the tidal deformability. Okay, and we'll talk a little bit about that more as we go on. But sort of still remaining quite holistic about this whole thing. If I look at this diagram, there's obviously branching here that can occur, and which path you take, whether this neutron star system collides immediately collapses to form a black hole. So that's this path A to B and then up to C, where as soon as it collides, you get this collapse to form a black hole, jets get launched, you see all of this electromagnetic radiation. But alternatively, a newly born neutron star can survive for some period of time, okay? And whether that neutron star survives for some period of time depends on the mass of the progenitor system. And it turns out we can actually measure those masses. So we have some idea of what the progenitor mass is, but what we don't know is what that maximum allowed mass is before these two stars will actually collide to a black hole. So you get this sort of situation where these two neutron stars collide, forms a new neutron star, which is massive. It's obviously a lot more massive than the initial progenitor stars. It can either then collapse into a new black hole, which is this path A, B, D, and then up to E. And if that can happen in anywhere from sort of 10 to 100 milliseconds, so really quite quick, but it's actually quite dynamic, and I'll talk about that in just a sec. Or otherwise, it can go to this path where it actually survives for a much, much longer time, and it can in fact survive for many thousands, even tens of thousands of seconds before collapsing to a black hole. And in that case, the neutron star is being supported by centrifugal support. Okay, the fact that it's rapidly rotating means it won't quite collapse to a black hole just yet, but as that rotation slows down, it will eventually collapse to a black hole. And we have evidence that we've seen systems like this, which I'm not going to talk about today, but you can ask me in the Q&A if people are interested. But alternatively, actually, there's a path where, in fact, these neutron stars then just survive, and they survive infinitely. There's no reason for them to ever collapse into a black hole, and they are these stable neutron stars, albeit massive ones. So again, the path that this takes depends on the progenitor mass. When we measure gravitational wave signal from that in-spiral phase, so from that phase of A and B here in this diagram, we actually get to measure those masses. So we have an idea of that, but what we don't know is that maximum non-rotating mass of neutron stars. How much mass can a neutron star support before it collapses into a black hole? That actual quantity is something that's, again, very dependent on the equation of state. So it's dependent on that real intricate knowledge of the nuclear physics of how the individual neutrons and protons are acting inside the core of the neutron star, or in fact how the deconfined quarks are behaving, if in fact there are deconfined quarks. So again, if we can measure this path either electromagnetically, so through traditional telescopes, or with gravitational waves, then we are going to have basically a measurement of that equation of state. And in fact, we're going to be doing this nuclear astrophysics. Okay, so to dive a little bit deeper into this, I mentioned that this phase here where this nice diagram D is this highly dynamic state. Maybe it only lasts for 10 milliseconds, 100 milliseconds. But it turns out that the gravitational wave signal from that is really, really interesting, and it's really intricate. And we can actually have some chance of being able to measure this. Now, it turns out that, best estimates at the moment say that up to about 79% of all mergers will go through this phase D here. So in fact, most binary neutron star mergers that happen we believe at the moment, will go through this phase, at least of this highly dynamic phase that emits lots of gravitational waves. And what I'm showing here on the left is just a schematic. You don't have to understand it at the moment. We'll get to understanding it sort of hopefully by the end of the talk. But you can see 4 different gravitational wave signals for this phase of the evolution of a system, but where the equation of state is different. And what you can see is that the structure of these gravitational wave signals look really different. And in fact, the dominant peak that you get, so you get this is the gravitational wave strain on the vertical axis. It's the gravitational wave frequency on the horizontal axis. And so the actual location of that frequency peak, at what frequency the main peak of gravitational wave occurs, really depends in a very intricate way on the equation of state. and therefore on the nuclear physics that we're trying to get at. So measuring that gravitational wave signal, which we haven't done yet, but we're, is a big aim in terms of what we're talking about here for OzHF, measuring that gravitational wave signal will give us this unprecedented knowledge of what the equation of state of nuclear matter is. But it turns out it's even better than that, because people for a long time have been saying, actually, the signal from the in-spiral should be correlated to the signal from in that post-merger phase. So in fact, I should be getting similar information from the in-spiral and from the post-merger. And in some sense, that's true, except that, again, there's this temperature dependence on the phase diagram. And so if I do have deconfined quarks, for example, or if I have, varying amounts of hyperons in the core, or all of these kinds of exotica that can occur inside a neutron star, it actually turns out that I can measure that by measuring the difference in the gravitational wave signal that I expect in that phase D from the gravitational wave signal that I've already measured in phase A and B during that in-spiral here. So this is from a really nice paper from Andy Bauswein from just the middle of last year, where basically he says, okay, if I measure the gravitational wave signal from that in-spiral part of the gravitational waveform, and that's sort of what a proxy of what's being shown on the horizontal axis, and I measure what's happened after the merger, then I should, if there's no exotic matter, then I should really expect this gravitational wave signal to lie somewhere along this grey band. Okay, and that's what you typically find. But of course, if there's a phase transition in the core to deconfined quarks, for example, then actually I'm going to be able to measure that. I'll measure the in-spiral, and here's just a couple of these green points are a couple of examples of this. I'll measure that in-spiral, and in that post-merger thing, I'm going to actually be able to tell, oh, look, there's some kind of phase transition happened here. So this is a really, really nice way of being able to actually probe the inside of those neutron stars, which you'll never be able to do with traditional telescopes, because when you're looking through a telescope, you're simply looking at the matter that's radiating high energy photons from sort of very far away from the neutron star, whereas the gravitational waves come from deep inside the core of the neutron star. So you really have this opportunity to probe the interiors of the stars. And so, this is a really powerful way to do that. But of course, to be able to do it, you have to actually be able to detect these gravitational waves in the first place. And we'll sort of get to that and talk about that as we go along. Okay, there's this whole other part of the phase diagram, and I'm actually, this evolutionary diagram. And you actually have some chance of measuring things like the equation of state here using various X-ray observations, other electromagnetic observations. I'm not going to discuss this in any great detail today. We've done sort of a lot of work on this in the past, and this is sort of one of the big topics that Nikhil, Saran and I are writing this review on as well. But, we're not going to talk about this in too much detail today. Okay, so we do actually, I mentioned earlier, we've measured a couple of neutron star in-spirals before. So let's look at that. There was this, hopefully most people on the call will know about this, but it's just too good an observation. It's the most beautiful observation in all of physics, in my very, very biased opinion. But I'll take you back to the 17th of August, 2017. What I'm going to show you now is both a gravitational wave signal that we detected on this day in August 2017 as part of the LIGO and Virgo collaborations. So LIGO are these two gravitational wave instruments, one of them in Hanford in Washington, up in the north of the USA, and the other in Louisiana and Livingston, down in the south. So separated by 1,000 kilometers. There's another detector over in Italy called Virgo, which is, again, separated by many thousands of kilometers from the LIGO detectors. All three of these instruments detected this same signal, which absolutely unequivocally tells us that it was came from somewhere out of the solar system. And in fact, we know that this came from 100 million light years away, and I'll talk about that as we go. But this gravitational wave signal came hit those detectors. And that's what I'm going to show you on this bottom plot here. So I'm going to show you the gravitational wave strain with frequency on the vertical axis and the time, just it's an arbitrary time where we set the time at 0 to being the time at merger, because we now know that this was a system of 2 neutron stars that collided. So what you're going to see is you're going to see this gravitational wave signal. It's going to come in low on the band, and then it's going to chirp upwards in this characteristic chirping sound that we're used to sort of talking about and seeing. But what was really fascinating about this event, we had seen signals, albeit shorter than this before, and things along those lines with LIGO. But Fermi is a gamma ray telescope, a space-based gamma ray telescope. And what I'm going to show you is simultaneously what Fermi detected while this gravitational wave signal happened. So you can see the gravitational wave signal here coming in. Fermi is detecting just a background of photons. You see this merger happened, and then all of a sudden there's an excess of these gamma ray photons. Okay, and this excess came about 1.6 seconds after the merger, which is a very interesting timescale. I'm not going to talk about that in detail again, but people can ask me if they're interested. And it wasn't just Fermi. This looks, this is obviously an excess of photons, but it's only an excess over the background by sort of a factor of 2, something like that, a little bit less. But there was actually 3 different instruments that saw at the same time an excess of gamma rays 1.6 seconds after the gravitational wave merger. But of course, that's not the entire story. Even if that was the entire story, that would have been absolutely beautiful and remarkable. But if you now progress 11 hours later, there's one of the really nicest sort of optical images that we've seen for a long time. This is on the left here, what I'm showing at the moment is just a Hubble Space Telescope image, not from this day on the 17th of August 2017, but from a few months earlier, so from from late April. And this is just of an ordinary galaxy with a very ordinary name, NGC 4993, because we're not very creative as astronomers. But, this is just the blob of a galaxy. There's some foreground stars here and things along those lines. It doesn't look like such a spectacular image. But this SWOPE telescope is a 1-meter telescope in Chile that 11 hours after this gravitational wave detection happened to be pointing in this right direction. And in fact, basically what happened was the LIGO detectors said, okay, there's somewhere on the sky, and they located a region of the sky about many tens of square degrees, and almost any person with a telescope who operated a telescope at that time started looking in that region of the sky. So SWOPE was the first telescope. There were 6 other telescopes that caught this basically within an hour of each other. But the SWOPE telescope took this beautiful image. And what you can see, the image didn't actually have that red arrow on it that's been put in afterwards to guide the eye. But you can see that this red arrow is pointing to a blob, a very small blob here, which is new. So when you compare this right-hand image to this left-hand image, you can see that, you can line up all of these other little blobs and they sort of correlate with the right-hand and left-hand plots. But of course, this new blob, new source of light is actually that the optical signal from that same merger. Okay, and there's lots of information that we can get at about that. And in fact, so this was 11 hours later. As I mentioned, about 6 different telescopes, all optical and UV telescopes, were looking in this direction. They all saw this. All of them observed this, and I'll show this very shortly. They observed this over the next 10, 11 days, saw the image fading, changing color, doing all of these beautiful things, which we can now sort of interpret in terms of the physics that was happening to the ejected material as it sort of shocked into the interstellar medium and things along those lines. But then, radio observations were taken, X-ray observations were taken. And in fact, there was a paper out just a couple of weeks ago showing even more X-ray observations of this source almost 1,000 days after the gravitational wave signal went off. So it's a amazingly remarkable event that we've been able to continue to witness over the last 3 years as it's evolved and dimmed and changed. And, you know, we're still learning so much about this system. What I want to tell you about is the sort of specifics relevant to what we're really discussing here. So if you look at, this is the gravitational wave signal that I showed before. Just from that gravitational wave signal, we can already get some indication of the equation of state, which is this thing that we're really trying to understand. So first of all, just from this gravitational wave signal, you can actually measure the masses of the 2 neutron stars that merged in this collision. Now, I don't want to go into too much detail in this plot. This is, if anyone wants to know, this is sort of, I'm at Monash University. This is our bread and butter. This is what we do. We take gravitational wave signals and we understand the astrophysics from those sources. And so, you know, this is a plot showing the masses of the 2 neutron stars that collided. And it turns out it depends a little bit about how much they're spinning and things like that, which is why there's 2 sets of contours here. But just looking at these, they're sort of garden variety neutron stars, which is to say they both have masses approximately 1.5 times the mass of our sun, which is sort of typically what you'd expect and things along those lines. So that's the masses of the 2 neutron stars. Again, we get that just from this gravitational wave signal from the in spiral. But we can also, as I mentioned, we can measure this tidal deformability, or in other words, we can get at least some handle on this equation of state. So the equation of state tells us, or these are the actual measurements. Don't worry too much about the specifics of the numbers, but this is sort of the tidal deformability, the amount that the neutron star is allowed to deform under the field of gravity from the other neutron star. The bigger the number, the less compact the star is. Okay, and so this primary tidal deformability is for the more massive neutron star. The secondary tidal deformability is from the less massive neutron star. And what you can see is basically we have some constraint from this gravitational wave measurement, but it's not great. Okay, you can see we're sort of, this is a 50% contour line. This is a 90% contour line. You sort of rule out some exotic equations of state that predict very big, sort of fluffy neutron stars, but you don't sort of get too much information. But that's okay. That, you know, this was the first ever measurement of a system like that. It's just fascinating. It's the first time we've ever had an equation of state measurement like this at all. So to get anything is really absolutely beautiful and absolutely fascinating. You can turn this into a measurement of what the actual neutron star looked like in terms of what we typically refer to as now a mass and radius diagram. So this is sort of a complicated figure, but it gets at the heart of really what we're trying to talk about here. And that is this is predictions for what neutron stars look like. And so what I'm showing here on the horizontal axis is the radius of neutron stars. And you can see that the radius of neutron stars is predicted to be anywhere from about 6 kilometers up to 20 kilometers, give or take a few, as a function of the mass of neutron stars. Okay, and again, we measure neutron stars with masses between 1 solar mass, so 1 times the mass of the sun, and about 2 times the mass of the sun, or a bit bigger. And each one of these curves is a prediction. So a nuclear physicist has gone away, done a calculation of the actual nuclear physics that occurs inside, or that we expect to occur inside a neutron star. And using that, they've been able to try and predict on this diagram what the mass and the radius of the neutron star should look like. And so what, you know, the sense that I want to give you from this is that there are so many different options for neutron star equations of state here. Each of these make different approximations or assumptions about the nuclear physics, but we don't know what's true. We don't know what's right. And in fact, you know, if you ask a nuclear physicist, they'd probably say, well, none of these are actually really right. And we need to do more and more measurements, and we need to actually understand the constraints of these things from various types of observations. Okay, so how do we do? We can take the measurements that I showed you on the previous slide, and we can put them into this sort of mass radius diagram. And before we do that, sorry, I meant to say, well, we've already got some measurements of this. We know that neutron stars have sort of a maximum mass, and that's what you can see. Each of these curves sort of turns over at some maximum mass. And so if you take, for example, this dark blue curve, you can see it turns over at about 2.3 solar masses. So if you measured a neutron star above 2.3 solar masses, then of course that would rule out that equation of state, because it simply can't predict a neutron star to have such a big mass. So we've already seen some neutron stars with masses up at around 2.1, 2.2 solar masses. That's what I'm showing here in the magenta color and in the green color. These are sort of the heaviest neutron stars that we've ever observed, just through typical observations of pulsars and things along those lines. This is the constraint that we get from the gravitational wave signal that we detected with 170817. So this blue region here is basically ruled out from that 170817 measurement. Okay, so in other words, all of these other equations of state, all of these other curves that exist in this region, and what's still a white region of parameter space, and also go through at least these magenta and green curves or lines, those equations of state are still valid. They still satisfy all of the observations that we have, at least to date, from these two systems. So you can see the gravitational wave observations are good, but there's a lot of work that we'll still need to do to actually understand this parameter space really deeply. There was some recent observations of an X-ray observations. They were sort of pasted on top here from a beautiful X-ray image, X-ray timing mission called NISA. They observe a pulsar. I don't want to go into too much detail of this, other than to say this is sort of their constraint in this parameter space. They sort of, anything that still fits inside this region is still satisfied by the by equations of state. And so that's actually really important, because that actually represents the best measurements to date that we have equations of state. But that's actually complementary to what we're talking about with the gravitational waves, because they're measuring a very sort of they're measuring systems in a very, very different way. And again, if people are interested, I can talk about details. What I'm showing now in green here is a prediction for, just if we continue to operate LIGO, what we expect to see when we have the first 40 gravitational wave events. And this is from a beautiful paper that a PhD student at Monash University, Francisco Hernandez Vivanco, wrote last year. And it basically says, let's predict what the first 40 gravitational wave events look like with LIGO and Virgo. And this is the constraints that we get. And what's interesting is they're somewhat complementary to these NISA results. So if I sort of toggle backwards and forwards, you can see that the results are very similar between those two. So just using LIGO, we're going to get very interesting results, but nothing better than what we actually already have using NISA. But this is, again, motivation for what we're going to do in the future. Okay, I mentioned that sort of post-merger gravitational waves are really important. So let's sort of briefly talk about them. What did we detect about post-merger gravitational waves from this 170817 event? And I sort of worked on this in a lot of details over the last few years. And I can summarize way too many hours of work into, we detected nothing, okay? We did not detect gravitational waves. Oh, and I apologize, this is missing half of a plot here. We did not detect gravitational waves from the post-merger of this event. But this is not a surprise. All of our predictions say that we don't actually expect to detect events like this until either they're much closer to us, which is not likely, or in fact, until our detectors get much more sensitive. Okay, and so I won't go into the details of these plots, because I've realized I'm sort of probably rambling already and running out of time. But this is all to say that we didn't detect anything. We didn't expect to. We didn't expect to detect gravitational waves, but this provides us with a really great opportunity to understand what we can detect in the near future, and provides really good motivation for this OzHF that we're going to talk about. We can learn a little bit about the post-merger, and what I'm showing here are those beautiful optical observations. You can see this is that blob that we talked about before. It started off very blue. It then, over a period of 6 to 10 days, it faded and became much redder. And so this is the spectrum of that over 10, 11, 12 days. It actually turns out the evolution of the color of that can tell us about what happened to that neutron star, whether it collapsed instantly to form a black hole or whether it survived for some period of time. The only thing that we can say for certain is it did not collapse straight away to form a black hole. Okay, so we believe that it was a short-lived or a long-lived neutron star. There's some really interesting evidence for both a short-lived neutron star that collapsed into a black hole on the timescale of order 100 milliseconds, but there's also evidence, somewhat contradictory, that a neutron star survived for even up to 100 days after the event. Some people now are even saying a neutron star survived even for 1,000 days after the event. The evidence is contradictory. That's great. That gives us an opportunity to continue to learn about this event in sort of unprecedented ways, but we obviously just need to collect more information and observe more events of this type. So I mentioned earlier that 1708-17 is not the only binary neutron star system that we measured. We have measured at least one more, and I'll very, very briefly describe these. There was an event, GW 190425. So we're creative in our naming. This is gravitational wave event. It was detected in 2019 in the 4th month. So that's April, on the 25th day. And for hopefully everyone knows, that's of course Anzac Day. No one in LIGO calls this the Anzac Day event other than me. So this is one man's futile mission to rename a scientific event. Whenever you refer to this event in the pub when you're talking to all your friends, please refer to it as the Anzac Day event. Let's get this rolling. But in reality, this event was actually fascinating. And again, people at Monash worked very hard on this. So Greg Ashton, who's a postdoc at Monash, wrote a lot of this paper, and Jingjiang Zhu, another postdoc at Monash, worked a lot on trying to understand and interpret this event. This was a really fascinating binary neutron star merger for lots of reasons, less relevant to sort of some of the things that we're talking about today. But it turns out this is the sort of same plot that I showed for 1708-17. This is the primary and secondary masses of this neutron star. And what's really interesting about it is that it's different from what we expect. And this is highlighted in this bottom right-hand plot here that shows the masses, the total masses, so the sum of the two masses of all of the neutron stars that we know of in our galaxy that are in double neutron star systems. So you go and observe double neutron star systems, or two neutron stars are orbiting each other. You measure their masses because you can measure the orbital dynamics, and you find that they all are sort of have very similar masses, and that's what's shown here with this grey histogram and the fit shown there. But this binary neutron star merger system, this Anzac Day event, actually had a mass that is a significant outlier to these. Okay, it was actually much, much heavier than we would ever expect. So that's really interesting. That tells us a lot about the formation mechanisms of systems like this, all of that kind of stuff. Really interesting, but less about the equation of state. We don't get substantial information about the equation of state here. This was quite a distant merger compared to the other one, things along those lines. So, but nonetheless, it's interesting. It tells us that, again, neutron stars merge in our universe very, very often, and I'll talk about that soon. So this was an interesting event. That's basically all I want to say about that. There was another one that was released just the other day, GW 1908-14. So this was, again, on August 14, 2019. What's really interesting about this one is that we actually don't know if this was a neutron star merging with a black hole, or if it was a black hole merging with a black hole. So here again is the masses of the two stars, or of the two progenitors. You can see that the more massive object was about 23 solar masses, 23 times the mass of our sun. But the secondary one was actually about 2.6 times the mass of our sun. And if you remember back to that mass radius diagram, 2.6 solar masses is either the heaviest neutron star that we've ever seen by a lot, by 0.4 solar masses, 0.5 solar masses, or it's the lightest black hole that we've ever seen. And to be honest, we don't know. We'd love to know. It's fascinating. We don't know how systems like this form, but this is part of the excitement of really opening up a new field, is that you get to observe these kind of new systems and then try and understand exactly what happens and exactly how they form, what it tells us about all of the nuclear physics, about the astrophysics, about gravity, et cetera, et cetera. So again, this is a fascinating event. I don't want to talk about it in too much detail, but again, this is all just to say that systems like this are merging really often in our universe. And so this provides us with a really good opportunity to probe deeper and to try and observe more and more of these. So it's at this point where I would make this an interactive talk, but of course I feel like I'm just talking to a computer screen. At this point I would ask the audience, so two neutron stars merge somewhere in the universe, how often, right? How often do two neutron stars merge somewhere in the universe? And the answer might actually surprise you. I hope it surprises you, because it's every 13 seconds, give or take. So every 13 seconds, two neutron stars merge somewhere in the universe. And we're just viewing such a tiny fraction of these neutron star mergers. So on the left, this plot I'm showing here is really just a schematic from another nice paper that Francisco wrote this year, where we looked at trying to work out if we can measure much bigger fraction of these neutron star mergers. And what you can see here is just a made up 200 seconds worth of gravitational wave data. And it's showing the gravitational wave signals that all of the gravitational wave signals that would be in that 200 seconds worth of data, or that might be in that 200 seconds worth of data. So obviously if there's 200 seconds worth of data, there's almost 10 gravitational wave signals from neutron stars in there, and they're sort of overlapping and, really interesting things like that. But, if two neutron stars merge every 13 seconds and yet we're only observing them every few months, this gives us an opportunity to say, okay, well, what is next in gravitational wave astronomy? Where are we going with this? And this is really getting to the sales pitch side of the talk, where at the end of this talk, I'm going to ask you to leave your credit card details. We just need a cool $50 million, maybe $100 million. So, just feel free to donate. That was a joke, by the way. So what's next in gravitational wave astronomy? Well, what I'm showing here is where we're at now in a sort of, in a typical parameter space that we usually think of. This is the gravitational wave strain. So how sensitive a gravitational wave instrument is as a function of the frequency. So the lower the curve is on this plot, the more sensitive we are. So this is about where we are at the moment with advanced LIGO. The design sensitivity for advanced LIGO goes down a little bit more. So this is where we hope to get in approximately the next couple of years. This is sort of, work is being undergone at the moment to really push that sensitivity down by sort of factors of 1.5, factors of 2, things like that. We have funding to build what's called A+, which is hoping to come online circa 2024, 2025. This is mostly funded, very minimal technology risk. It's basically improvements over what we have now using the current vacuum systems, using all of the current systems. Hope to just push that sensitivity down with the current LIGO down by another factor of a couple. But then after that, we're sort of a little bit of a loss. There's unfunded, but sort of uncharted territory, but designed systems, 2 of them in particular, one called Cosmic Explorer, the other called Einstein Telescope. And what they hope to do is they hope to get another sort of factor of 10 in sensitivity. And once you get another factor of 10 in sensitivity, it turns out with gravitational waves, sensitivity goes like, the inverse of the distance that you can see. It's not the inverse of the distance squared like you might expect, but it's the inverse of the distance. So you can actually start, if you get an extra factor of 10, you can actually start seeing really to the very early parts of the universe, and you start actually seeing all merging black holes and neutron stars throughout the universe, or at least a large fraction of them. But this is really, it's not funded. There's design study funds and things like that, but there's a lot of technology issues that are really uncharted at the moment. So our proposal is a halfway house in between these two things. Our proposal is this thing that we're calling OzHF. The HF stands for high frequency, and this is the proposed design sensitivity curve that we're really talking about. So, and I'll get into the details of this, but this is in the dark red here. What you can see is up at high frequencies, so up at a kilohertz and more, we really hope to get down to that same sensitivity that people are suggesting we should be able to get to by the late 2030s or even early 2040s. And I'll tell you why we're going to do that in a short second. But those sort of cosmic explorer type missions or type instruments are really billion-dollar scale instruments. They are absolutely, you know, they cost more than just an arm and a leg. What we're proposing is something that's more on the order of $50 to $100 million. It provides technology development for these full 3G experiments, but at a tenth of the cost. And the reason that we can get those costs down so low is because we don't care about this low frequency sensitivity. So you can see that the sensitivity here in this low frequency regime at the sort of 100 Hertz region, it really, it's much worse than for the full third generation detectors. But that's okay. What we're basically proposing is that this OzHF will live in a network of A+. So A+ gets designed and built circa 2024 and gets operated through to the 2030s. We're proposing that OzHF is also built on that timescale, hopefully built by late 2020s, early 2030s. So it's operating at the same time as A+. And what that means is that we have that broadband coverage going from sort of tens of hertz up to a kilohertz or a few kilohertz, but you've just got that broadband coverage in a couple of different instruments, okay? So let me explain exactly where the science case comes from building this. So I've sort of simplified that last diagram now. I've just kept the OzHF curve. So this is the one that we're proposing. The A+ sensitivity is in blue there. So we're proposing basically that these two, A+ and OzHF, exist at the same time. And in magenta is this, far future thing that sort of requires technology development and things like that. So when I have two neutron stars and they spiral in on one another, this is the typical signal that I would expect to see, okay? So when the two neutron stars are far from each other, they're coming in like this until they eventually merge, which is not being shown just yet on this diagram. So ignore this sort of big, this edge that it goes off here is what would happen if it was two black holes, not two neutron stars. But really, when we're talking about those tidal effects to measure the equation of state, I'm talking about the effects that occur up here, up in the sort of above 500 Hertz regime. And so what you can see is the sensitivity above that 500 Hertz regime of OzHF is much better than of A+. So you're going to get a much better measurement of the tidal effects and therefore the equation of state from OzHF than you would ever hope to get from A+. And I'll quantify this in just a second. When I add that post-merger signal, that post-merger gravitational wave signal that we've been talking about, where I really get a chance to measure that hot equation of state, that's all of this sort of junky, messy bit that's up here, but it's really up in the kilohertz regime. It's up at sort of 2 kilohertz, even up to 3 kilohertz. And so this is really where OzHF thrives. OzHF will be able to detect this because you can see you're a factor of a few better in sensitivity than you are with A+. So in this signal, for example, A+ would marginally and probably not measure this, and I'll quantify this in a second. A+ would probably not measure this, but OzHF would. And OzHF would not just measure it, but we'd actually be able to learn about quantum chromodynamics. We'd be able to learn whether there are deconfined quarks and things along those lines. So I'm certainly running out of time, so I'm going to skip that one. I'm just going to go to this slide. This is a schematic now, or actually the plot on the bottom right actually quantifies what I was just talking about. So in black, I'm showing the average number of expected detections when you have an OzHF instrument for this post-merger phase. And it turns out that you're going to actually detect on average, one a year. Okay. Whereas if I don't have an OzHF, this plot tells me that I'm going to detect one every 10 to one every 100 years. So in other words, I'd have to wait approximately 50 years before I could ever hope to detect a post-merger remnant if I don't have OzHF. If I do have OzHF, then I'm going to detect on average one a year. It may be up to many a year, but it may be, of course, one every couple of years. Pardon me. So that's really the sort of take-home message, at least in terms of that. What is this instrument? It's 4-kilometer arms. It's an interferometer. Getting into some of the details here, it's got 74 kilogram silicon test masses. It's cooled. The whole point of this is to say that there is no real, or we're minimizing the risk in terms of technology, but we are providing a location to explore third generation technologies at the same time. So we neglect that low frequency isolation. That's the thing that keeps the cost down. The preliminary design curve basically tells you that you're limited by quantum noise through most of the band. I'm not going to go into too much detail about this plot, but you're limited to quantum noise through most of the band. You've got a little bit of sort of suspension thermal noise, but all of this is to say that we've modeled this really, really well, and we understand all of the various noise sources. Okay, I'm just gonna, this will be my sort of last slide, and then I'll flick to the end. This is from a white paper that we wrote that is on the archive, and if anyone wants to look at it, it's easy to find. Just search for ground-based gravitational wave astronomy in Australia. Basically, this is sort of the timescale that we're looking at, where you're talking about construction and commissioning by sort of late 2020s, early 2030s. And this would then pivot from an OzHF into a full third generation Cosmic Explorer South, sort of in the later years. I will basically leave it there. OzHF, this is, the paper is under review at the moment. We're going to have a press release hopefully next week. It's being announced as well. The Australian Decadal Plan for Astronomy is having a midterm review at the moment. And one of the big priorities that they've put in that Decadal Plan is actually OzHF and building this instrument. So, we're starting to get that support, that impetus happening. Hopefully, people on this call are on board, and I'm more than happy to sort of answer any questions about it. And I will leave it there and say thank you very much for having me. Thank you very much to the AIP.
Awesome. Thank you so much, Paul. Yeah, if people are interested in the next talk in the series, the next host will be the ARC's Centre of Excellence for Quantum Computation and Communication Technology, and their talk will be on the 6th of July. So those details will come up in the AIP bulletin and on social media when those details are set. So we do have some questions. Thanks everyone. If you have another one, you can type it in. I'm not sure how many we'll get to, but I guess probably leading straight on from why OzHF in Australia. John's asking, why would Australia be a better location for the proposed new observatory than anywhere else? Does distance from other observatories help?
Yeah, this is a great question. So the answer is truthfully no. OzHF does not have to be in Australia, but so because it lives in a heterogeneous network, you need the distance between observatories to occur for the low frequency ones, but OzHF can live anywhere on the planet. But if you want to build, so the full third generation detectors, the Gravitational Wave International Committee wants 3 of those. Okay. And there you want that sort of the equally spaced locations all across the globe. So there is a call to have a Cosmic Explorer South. And so if you want to build a Cosmic Explorer South, the best way to do that is to start off, we believe, is to start off with an OzHF and then sort of pivot that into a Cosmic Explorer South.
And I guess kind of related to that, Mark's asking, could OzHF be fitted to existing observatories such as LIGO or Virgo?
Yes, it would need some changes, absolutely. And this is one thing that's certainly a possibility. You know, there's a 600-meter geo in Germany where you could possibly use the existing vacuum tubes and things along those lines. So yes, these are all options that are sort of being explored globally.
Awesome. Someone also wants to know, how sensitive will LISA be compared to A+ and LIGO? Yeah,
good question. So it's not a question of sensitivity per se, or sensitivity comparisons. So LISA is sensitive in a completely different frequency band. So where we were talking about 10 hertz to 1,000 hertz here, LISA is sensitive to 10 to the minus 3 hertz, give or take. And so what you're detecting there is different sources. So you're detecting sort of two white dwarfs that are in spiraling, or the early phases of two black holes and things like that. So they're complementary experiments in that sense.
Awesome. Probably got time for two more. Sean's asking, is there a Cepheid variable analogy in gravitational waves to calibrate distance for redshifted mass? Great talk, by the way. Cheers.
Oh, fantastic question. So if I understand the question, and maybe I don't, but I can say a bit. So gravitational waves provide an amazing way to do cosmology. And so basically what you have is, and we've started to do this with 1708-17, and the more observations we get, the better we'll be able to do. But actually you can measure the distance and the redshift independent of the cosmic distance ladder. So you don't need Cepheid variables, you don't need supernovae, things along those lines. You actually just get the distance and the redshift by measuring the gravitational wave signal, and you get the redshift by getting the counterpart. Or there are a couple of other ways which I can talk about if people want to contact me offline. And so it provides a really complementary way of doing cosmology without having to rely on that cosmic distance ladder that, you know, supernova cosmology relies on, for example. I hope that answered the question, but maybe not.
Okay, last one, easy one. Corbin wants to know what got you interested in gravitational waves.
Oh, good question. Yeah, so I did my PhD more on just hardcore general relativity. So I sat there with pen and paper and tried to solve Einstein's field equations, which I now realize was a stupid thing to do because they're really hard to solve. And sort of from there, I was always just interested in really strong field gravity, I guess. So, you know, I grew up reading Kip Thorne's books and Roger Penrose's books and Stephen Hawking and things like that. So I was always interested in black holes and things along those lines. And so I guess from the time I was doing my PhD in 2008, I realized that if you're ever going to observe a black hole, you're going to have to do it through gravitational waves. And so that was just where the interest grew out of that.
Awesome. Thank you so much. We're going to wrap it up there. It's 11 o'clock. Big thanks to Errol. Thank you to AIP for hosting, and I hope people enjoy the next talk in this series.
Thanks, everyone.